Okay, so I hope the screen is visible to all of you.
Yes.
Yes.
Yes, sir.
Okay, cool. So, yeah, so what we were doing was we started off with neural networks yesterday. Okay, and these are like popular models for classification as well as regression. This is something that's used. And what we saw was, you get the neural network by bringing together several units of the perceptron. So basically, you have like several layers coming together. So your starting layer. So I'm sorry about the diagram. It's been like very cluttered. But please ask if something is not clear to you. So the starting layer. This was like layer zero, right? So this was the initial layer where you had like all the inputs. So the x1 to xd, the features. That was what formed the zeroth layer. And then we had these weights. Okay, so wij, more specifically wij, which connected a unit from layer l minus 1, wijl. So this superscript denotes the layer. So neuron I in the layer l minus 1, it connects it to neuron j in the layer l. Okay, so this particular one that you see was W11, and this one that you see here was W21. Okay, and the superscript 1 denoted that it's connecting to neurons in layer 1. Okay, so that's what these weights denoted. And what we had this quantity ZIL, which was the value obtained by multiplying these W's and the outputs from the previous layer. So the outputs we denoted by A's. Okay, that was the notation that we used. So A10 is the output from neuron 1 in layer 0. So all these units are called neurons. And in layer 0, neuron 1 gives you the output A10. And similarly, so AIL more generally is the output from neuron I in layer L. Neuron I in layer L. Okay. And the way you compute AIL is by means of an activation function, which we called as H. So H acts on ZIL to give you the activation function. So you can think of this neuron having two parts. So one part is where you compute the Zs, so this quantity, and the other part is where you compute h of that, where you apply the activation functions that gives you AIL. And so you keep doing this for some L layers, capital L number of layers. And finally, the last layer, L plus 1 is the last layer, and that's what gives you the outputs, okay, the final outputs, which you actually observe in your training data. Okay, so this was the configuration of the neural network. So this is like the most general form of the neural network, where you have these 1 to L. These are all the hidden layers, right? So all these from starting from here all the way till this point, these are the hidden layers because you don't observe these at all. The layer 0 outputs, so those are actually x1 to xd that you observe, that is your features. And the final layer consisting of A1, L plus 1 to whatever the number of neurons you choose here. So if it's a classification problem, you can fix this as the number of classes. So that many neurons in the last layer, those are actually observed. So that is called the output layer. Okay, so this is what we saw. This is the configuration of the neural network. Now, there are different possibilities for choosing the activation function, different possibilities of networks. So sometimes there are some networks where you take the output. I mean, the output also it affects some. You have some kind of a loop like this. Okay, so that can also happen. So those are like these recurrent neural networks. Okay, so there are different possibilities here. But what we will look at is just this kind of a directed acyclic graph structure. Okay, so this is the initial neural networks that were introduced. Now, all the concepts that we see here are also applicable for, if you have different network structures. Okay, so what we'll discuss is for the most general structure like this. Okay. All right, so these were the various components. And then what we wanted to see is like, okay, so these W's are there and there are these B terms. So these B's are called the bias terms. Okay, so like what we had in perceptron. And the ultimate goal is to learn these W's and the B's. so that it fits your training, if it fits your data well. Okay, and so you are enrolled with some training data for this. Okay, and so this is your training data, and what you have to do is you have to use this training data, which is composed of these xy pairs. So x's are vectors, so this is your feature, x is an RT, and then you also have which class it belongs to. If it's a classification problem, if it's a regression problem, you have a real number here instead of a class. So let's just look at classification. So what you can do is, if you have the class label, you can transform it into a vector. This is actually like an indicator vector with a 1 at position I and zeros everywhere else, if you want to represent class I. So these kind of tuples you have of the features and the class, and based on that you want to minimize a loss function, which is a function of your parameters. So W and B are the parameters of the neural network, and you want to find this. Okay, so this is the parameters. These are the parameters of the neural network, and you want to find this. And the loss we defined was in terms of the last layer, right? So finally, what you're going to get is the AJL plus ones in the last layer, and you want to see how different those are from the YJs. So YJs are given to you. Okay, so this is for one training point. So AJ, I mean, so this inner summation is for one training instance. Now, what you do is you sum over all the points in your data for all the examples that you have. You want this to be minimized. So your overall loss is a sum of all these individual instance-wise losses. Okay, and our objective is to find the W's and B's which minimize this loss. Okay, so how do we go about doing that? And what we saw was a gradient descent algorithm, where each time you start off with a W, and then you move W in some direction. Okay, and the particular direction was the negative of the gradient. So this is the function that you want to minimize. You take the gradient with respect to W. Now this is going to be a big vector. Okay, so it will compose, it will be, this will have all the, Wij's from every layer. So this is going to be a vector of all these things. So for all L is 1 to L plus 1, and also J, so Ij also, right? So all these are going to be there. So I will, so I is the previous layer. So 1 to N L minus 1, and J will be like 1 to NL if there are NL neurons in layer L. Okay, so this many parameters will be there. So this gradient is going to be a vector of a very large size, and you have to find this, and that is the direction in which you will move. And there is also it's multiplied with some quantity eta, which we called as the step size. So that's the terminology in optimization literature. Now in machine learning, this is also referred to as the learning rate. Okay. So this is kind of like what you saw in Q learning, right? There was in Q learning and also temporal difference learning. There was an alpha times something plus one minus alpha, or the old value plus alpha times some difference. So it's exactly like that alpha that you had in Q learning or temporal difference learning, the same concept. So this is called the learning rate. And what you do is you keep doing these updates till some convergence notion. Okay, so now one convergence notion that I told you was maybe you can see how much the W's and the B's change. Okay, this is one possibility. But one thing to note is this is not set in stone. There are different options here. So another option, another thing that people do is you, instead of seeing like how much the W's change, you see how much the J, the function, the new function, like J of WT plus 1 minus J of W. You see that, and you see how much that changes. If that doesn't change a lot, then you can stop, something like that. So there are different convergence notions possible here. Okay, and so generally, I mean, this is something that people experiment with, and so that's not a fixed. It doesn't have to be one particular thing. You can choose what works for the application. Okay. Now another thing is that in these machine learning kind of applications, there is some data, right? So you have a training set, and there's something you can do using that training set towards to see whether you have really converged. Okay, so that is something I will probably tell you a little later. So let's try to look at this algorithm and how we go about these steps. Okay. So were there any questions from yesterday's class? So this was just a quick recap. I just want to check whether you're all okay so far. Can you just type or speak out? Okay. Most of you are very quiet, so I don't know what's going on. It was all clear? Okay, fine. So, all right. So, where we left off last class was I was telling you that, okay, the gradient descent algorithm is what is, it has some guarantees for some kind of functions. What people do is also this method called stochastic gradient descent. So what this is particularly applicable in machine learning kind of applications where your j, right, your loss function is a sum over several training instances. So instead of doing this kind of an update where you compute the gradient for you consider every training point here and compute the gradient for all these few, instead of doing that, what people do is to get a little faster. So this can be very slow if your w is very large. Okay. So another tweak that people do is that don't take all of jwb. So what you do is you define something like this. So jwb for a particular instance, so for a set like this. Okay. And so just if you take only one training instance, this is just going to be the same quantity here, right? This part aj l plus 1 minus yj square, you just take that. Okay. aj l plus 1 minus yj square. So you just take this one, and what you do is maybe let me just write the steps again. I'll just copy this part and yeah. So this was the original gradient descent algorithm. So instead of doing, working directly with, all the training examples, what you do is you just take one example, okay, at a time. So this, the gradient, I mean, this function, you just consider as though this was the only point that you had, and you keep computing the gradient only for that training instance you involve it. And then what you do is you'll have one more step here. So you iterate over each training instance. So for each training instance, okay, what you do is for each xy in your b train, you keep doing this. Okay. And then what you do is you finally do this till as many times as you need, so till convergence. Okay. So this is also something that people do. Okay. And there are different variants. So instead of going systematically over the training set, maybe you randomly pick training set, examples. So that all is like flexible. So, but the thing is that this update, so that it becomes faster, you do an update for each training point. So when you take the gradient, you only look at one training point here instead of looking at all points. So that is a stochastic gradient descent algorithm. And another, there are different variants. So instead of just looking at one training points, maybe you want to look at a batch. Another option is look at a particular batch of examples, a smaller batch. So not all of D-train, maybe a batch of maybe some 3 or 4 examples. So something like that, maybe a batch of some K examples you can take instead of the entire training set. Okay, so this is all done just to get some speed. And so I just want to show you one visual on this. So this is how it works. So if you do a gradient descent, so batch gradient descent means like for the entire training set. So that's what they have referred to here. So this can be how, as with iterations, for each iteration, how J of W, how it behaves. So this is one possibility. In gradient descent, you're guaranteed that at every step, the loss function improves. Okay, but what happens in stochastic gradient descent or this mini batch gradient descent, where you don't do with every example at a time? what can happen is you will end up, sometimes you improve, sometimes you get worse, and so on. But the general trend is towards a decrease. Okay, and finally it converges. So this is, in some sense, it's actually found to be faster. It performs well in practice. So that's why people go with this. Okay, so now what we'll do is, in this neural network also, what you have to do is, you have to compute these quantities, these gradient vectors. And how do you do that? Okay, because the network itself looks very complex. There are, basically all these wijs. These are the variables, and you need to find the gradient with respect to all these w's. So how do you do that? I mean, it looks very cumbersome, and there are a lot of, dependencies that are going on here, right? So how do you efficiently do this? Okay, so that brings us to what is called the back propagation algorithm. Okay, this is the back propagation algorithm. And so what happens here is, this is just exactly stochastic gradient descent. But what you do is, you have some nice way of doing these updates. Okay, so it's in some sense a way to, achieve this computation of these gradients. Because what happens is, an example like where you use, neural network for images is like, maybe let's just do that example and see how big the network can be before we go into back propagation. So typically images are represented using, some kind of a matrix like this. Okay, so that is your x's, right? So you'll have a matrix like this. So that's all your pixels. Okay, so if you're trying to do some image classification, what you will have is your input is going to have a matrix like this with several pixel values. And so this can be something like, an example in one of the references is, this is like 28, and this has 28 rows and 28 columns. So what you have is, each element of this matrix is there. Okay, and so that is a feature. So this is like x1, this is x2, something like that. Okay, so your dimension of this is like 28 times 28. So this is the number of features. Okay, so number of features that you start with is this. So this is your first layer. So x1 2, what is this number? Can somebody tell me? 28 times 28?
784.
784. Okay, so x 784. So this many features are there. So this is your layer 0. Now maybe your layer 1 has about, say, some 15 layers. Okay, so this is 15 layers. And maybe you just want to have 2 layers. Okay, so suppose you want to do that, and this also is like 15 layers. And finally your output class labels, maybe it's like 10. Okay, so there are 10 classes here. So this is like, your digit recognition, right? That kind of example. So there are numbers, all these images are from 0 1 up to 9. And so your classes are these 10 classes. Okay, so 0 to 9. So one output for each of them. Okay, so suppose this is your network. Okay, so there are not too many layers, just 2 layers. Okay, so the number of weights that you will have, right? So all these, so you're considering the most general network, where you have like connections between every neuron in a layer to the next. Okay, so here what you will have is the number of weights. What will be the number of weights in this layer? In layer 1. So this is like W111 all the way up to W784 15 1. Okay, so what's the number of weights that you will have in this layer?
784 into 15.
Yes, 784 into 15. So this number is, I don't know, I think it's roughly, can somebody tell me roughly how much this is?
11760.
11760.
11760. Okay, fine. So this is the number. And so now in the second layer, you have 15 to 15, right? So all these connections. So how much would this be? How many weights would come here?
225.
225, right? So this is 15 into 15. And finally, in the last layer, you have 15 times 10, right? So this would be 15 into 10. Okay, so this is 150. So totally, you have like this many weights. Okay, and also you have your those bias terms, right? So this will have again plus a 15 because those B's, right? So B15 from B1 to B15, and again B1 to B15 here. Okay, so all these will come into play. So overall, like this will be roughly, I think, about maybe some 12,000, right? So something on in this range, right? So this is as big as your weight vector gets, even when you have just two layers with not many neurons. Just 15 neurons in each layer will give you such a huge, collection of weights that you have to learn. Okay, so what is an efficient way to do this, right? And given that there are a lot of dependencies across, what is the good way to do it? And that's what is the backpropagation algorithm. So let's just see how we evaluate these gradients. Okay, so that's the crux of the algorithm, right? The stochastic gradient descent, you need essentially you need these. Once you have these gradient vectors, you can just proceed by plugging this in. Okay, so let's just take one training example. So consider the training example xy. Consider xy, just a single training instance, because your stochastic gradient descent is going to just look at one training instance. And let's try to compute these dou j by dou w's. Okay, so let me just zoom into one of these layers. So suppose I'm trying to compute something like this, dou j by dou wl in the lth layer. So what happens is you have this neuron in layer L. Okay, so let me call this, the output is AIL. So this is neuron I. Okay, so neuron I in layer L. Okay, so neuron I is what I'm trying to focus on now. Now how do you compute the values within neuron I? This output, there were two parts, right? So there was one part which was ZIL and there was one part which was AIL. Okay. Now, how was ZIL computed? So it depended on layer L minus 1. Okay. And so there were a couple of things here in layer L minus 1. So generally there were several units. And let me call this neuron J in layer L minus 1. So here there was an AJ L minus 1. So A1 L minus 1 all the way up till, N L minus 1 neurons here. And so what happened is ZIL, right, was computed like this. You had all the J's in the previous layer from 1 to N L minus 1. We had the weight here was WJIL. Okay, so that's what we followed. So WJIL times AJL minus 1 plus this bias. So there was a bias here of BIL. Okay, this is how we did. This is how Z's were computed. Okay, and finally the AIs were, we use some activation function. So let us, for the purpose of this class, let us take the sigmoid function. Okay, so sigmoid, so this was defined like this: 1 by 1 plus e power minus ZIL. Okay, so we'll just focus on this way of computing things. And now you want to compute, say, this particular gradient. So for this value, right? So WJIL. So what you want is dou J by dou WJIL. So let me just try to compute this. Okay, it's just focusing on a small part of the network. Okay. Now, what is useful here is the chain rule for differentiation, because there is a Zi which makes use of W's, and there is again an AI which acts on this Zi. Now, what is going to happen is after this, you have a layer L plus 1. Okay, and here there are many neurons. So let me look at a particular neuron S. Okay, neuron S in layer L plus 1. So of course there are going to be weights everywhere. Okay, and this one is going to be WISL plus 1. Okay, so all these neurons in the next layer are going to depend on AIL, which in turn depends on ZIL and which will in turn depend on WGIL. Okay, so that's the way the information goes. I mean, that's how the derivatives will matter. So what you do is, if to find WGI, the derivative with respect to WGI, what immediately uses WGI is the Z's, right? So this you can compute by using the chain rule, like you try to see dou J by dou ZIL times dou ZIL by dou WJIL, right? Because WJIL, the only place where it comes is in the computation of ZIL. Okay, if you have some other neuron here, you're going to have another weight. So something else here will use WJ. If this is neuron I dash, this is going to be WJI dash L. Okay, so WJIL only plays a role in the computation of ZIL, and so you can do this. Okay, so this is the chain rule. More generally, if you have a function like this, f of g of x, and you want to find the derivative of this with respect to dou x, I mean, derivative of this with respect to x, recall, like from your calculus lessons, you would have seen that this is dou f by dou g times dou g by dou x. Okay, so it's basically the same thing that's going on here. So you take the derivative with respect to z and then dou z by dou w. Okay, so so I hope this is clear. Like I hope the chain rule you all understand how to use it, right? Is that clear? Like, are you all familiar with the chain rule?
Yes, ma'am.
Yes.
Yes, ma'am.
All right. Okay. So, so what we'll do is this quantity here, dou j by dou z. This is something we will just maintain this throughout. I'll call this delta IL. We'll come to how you compute this one. Let's look at the other term now, dou zi by dou wjil. So basically this part, the derivative of dou z with respect to with respect to wjil. So can you tell me what that is by looking at this? This is the update, right? This is the how you compute zi. So what is this going to be?
AJ of L minus 1.
Yes, exactly. So it's just aj of L minus 1. AJ L minus 1, right? So that's just about it. And similarly, now the same thing you need for dou J over dou BIL also, right? So this is going to be exactly the same thing. You will have dou J by dou BIL times dou J by dou ZIL times dou ZIL times dou BIL. Okay, so this part is again delta IL, and dou Zi by dou BIL is what?
1.
1. 1, exactly 1. Okay, so this is just delta IL. Okay, so this is, so you have some way to compute it. Now, of course, you have to figure out how to compute delta ILs. So one thing to note is there is also a dependence on AJL minus 1. So if you're trying to compute a derivative for these points, there is a dependence for something which came before. Okay, and this is going to be the case for every layer. So any layer you take, this is going to be the general form. So how the backpropagation algorithm will work is, let me just give you an outline of it, and then we'll go into computing this delta ILs. So since there is a requirement to compute AJL minus 1 from the previous layer, to compute WLs, you need something the previous layer. What you do is you first cycle through the whole network. I mean, not cycle, you first traverse the entire network, store the Zs and As, and you go all the way till the end. Okay, and then starting from the last layer, L plus 1, you come backwards. Okay, so let me just maybe write this down. So yeah. So what you will do is there'll be this entire network, right? There's a whole lot of things, whole lot of connections, all this going on. And so this is layer 0. And finally, you have a layer L plus 1. Right? So how it works is, first you start off with these the initial values, so A1 to this is AD, and this is layer 0. So these values are these. So these are just your initial features. So what you do is you start going. So now you're fixing one point, x, y. Okay. And then what you do is for each layer, for layer L equal to 1 to L plus 1, what you do is you compute ZIL. Okay, so ZIL, you know how to compute. So it's just this, right? So this value. So compute ZIL. So compute ZIL and AIL. Okay, store these. So this you can do because you're going from here. Once you finish this layer, I mean, after you finish layer one, you will have the ZI1 and AI1s. All these you will have. Now use that to compute for the second layer and you keep doing this. So do one pass. So that is like you traverse the network this way. So this is like a forward pass of the network. And then what you want is the gradients. So to compute the gradient, because you have this dependence on the previous quantities, right? AJ L minus 1. What you do is you start from the end. Now you compute for layer L equals L plus 1 to 1. Okay. So here what you do is you try to compute these. So compute this delta IL. So that I will tell you how to do it. So compute delta IL. Okay, so I think I need again more space. So now in each layer there is this I, right? So for I is, so basically if you look at layer L, I mean there are these I's which have to come from L minus 1 and J's which come from layer L. So for I is 1 to NL minus 1 because there are NL minus 1 neurons in layer L minus 1. And for J is 1 to NL. Okay, so that is layer, so this is layer L and this is layer I. Okay, or did I write? Okay, so let's just take it as maybe let's reverse the indices because I've just written it as that way, dot J by dot WJI. So J is for the previous layer and I is the layer L. So here what you can do is now you can compute dou J by dou, I mean, so first thing is you compute delta IL, compute delta IL. Okay. And then what you do is you also compute dou J by dou WJIL and dou J by dou BIL. Okay, so this you compute and you also have like, I mean, what you do is you just, and you can, with this you can now do stochastic gradient descent. So you initially had a W. So you started off with a random W and B. And then what you do is you just do this step, WJI, the particular value alone, you update that. Okay, minus eta times dou J by this value that you compute here. Okay, so this is nothing but delta IL times AJL minus 1. And this you have already computed. AJL minus 1 is computed in the forward pass. Like as you went forward, you did this. So there's a forward pass and there is a backward pass. So that will give you the gradients. Okay. Is the flow of this algorithm clear? Are there any questions on this?
No, ma'am. Please repeat once again.
Okay, fine. So, okay, so do you understand this part, the dou J by dou W's and dou
Yes,
J
ma'am.
by W's? This computation is fine, right? Of course,
Yeah.
delta I's, I will tell you in a minute how you compute this.
And implementation of the algorithm.
The implementation of this, right? So because you need there is a dependence of the gradients with the previous layers outputs. So the gradient with respect to Wij, this particular quantity, is going to depend on a1 to a nl minus 1. So the nl minus 1 neurons in the previous layer, it's going to depend on the outputs from all that. So what you do is in two passes. So you keep one pass where you start from layer 0 and you go all the way up to layer L plus 1, which is the last layer. And as you do that, you keep computing ZIs and AIs. So each neuron has a ZI and an AI value, right? So the ZIs and AIs, you compute it using these equations, right? It's just multiplying with W's and B's. So what you will have is you will initially start off with some W and B. right? So it's exactly the stochastic gradient descent. So it's basically this algorithm itself. But now what you're doing is this part, the W equals W plus eta of this, right? I'm just telling you how to do this, how to implement this part. So that's what the back propagation is. So now what you have is you have a W and B, which you initially started off with. And now you compute the Z's and A's. Okay, so that with the W's and B's that you have, you can compute the Z's and A's for every layer. And you finish this. You do one forward pass, compute all these Z's and A's, keep it with you. Now you start from the end. You start from layer L plus 1 and you go back all the way to layer 0. Okay. And in doing that, you compute this gradients. So the gradients you compute in the reverse. Okay. So starting from L plus 1 to 1. And what you need is these WJIs, right? So for each layer, what you're going to have is WJIs, okay, where J is from the previous layer, right? So this was layer L and the J's came from the previous layer and the I's were in this layer, right? So what you do is you fix the J's and the I's. So you have to iterate over this. You need to compute that many dou J by dou WJI's. And what you do is you compute the delta ILs, okay? And also, so delta ILs, I'll tell you how you do that, okay? And you compute these quantities now, okay, because once you have the delta ILs, what you just do is it's a multiplication with AJL minus 1. And for BIs, you directly have the dou J by dou BIs, okay? So you just do that. And now you can do this update just for that particular JIth element. Okay, so WJIL alone, you can do this update. Okay, so ultimately what you wanted to do was this the entire vector you wanted to update in this manner. Now what you're doing is you're doing one component of this W vector, you're going to update in this manner. Okay, and you keep doing this. So BIL also, you do it in this manner. So BIL minus eta times dou J by dou BIL. Okay, and this you do for the entire network. So you start from the end and you come all the way down, and that's how you update your W's. Okay, Rishabh, you understood now?
Yes, ma'am.
Any confusion in this thing, something that's bothering you?
No, ma'am. I will once again study, then it should be more clear.
Okay. I mean, you can ask, if there's some particular part which, you don't follow here, we can try to resolve it. Many times it will be a small thing which bothers and then it kind of escalates, right? So, um,
No, ma'am. Means once I will again study, then I think it's more clear.
okay. All right. All right. Okay. So, I mean, this is the general flow of the back propagation algorithm. And I don't know whether what the others feel like. How is it clear or not? Like, Advait,
It's clear, ma'am.
it's clear. Aditya, Aditya Jain, it's clear. Okay. I don't know. Maybe some of the others also. I just want to hear. Gunjan, is it okay?
Yes, ma'am, it's clear.
It's clear. Okay. Karthik, okay. Karthik is not responding. Satvik, you follow this? Is this okay? Okay. Satvik is also quiet. See, I would urge all of you to. Okay, I mean, I know this takes some time to grasp it, but please go through it and let me know if something, whatever I can do to make this clear, I will do it from my end. Okay. Um, okay, so maybe let me just do the last step, which is computing these delta ILs. So that is basically the way we define delta IL is dou J by dou ZIL. Okay. So again, you do the same thing. It's basically chain rule itself. So ZIL is getting used by AIL. So what you can do is you can just write this as dou J by dou AIL times dou AIL by dou ZIL. Okay. So it's the same principle. And now for dou AIL by dou ZIL, so this is the sigmoid function. So here, let's just do this computation first. So dou AIL by dou ZIL. If you want to compute this, AIL, remember this is just 1 by 1 plus e power minus ZIL. Okay, so can you tell me what this derivative is? So what you're trying to do is dou AIL by dou ZIL. So how do you take the derivative with respect to this quantity? Okay, people have to
Then it
recollect
will be
this. Yes, tell me.
e to the power minus ZIL
E to the power minus ZIL
upon 1 plus e to the power minus ZIL to the whole square.
power minus ZIL and the whole square. Okay, so let me just break this down for those of you who might be still figuring it out. So the derivative would be like you first take the derivative, the overall derivative of this function. So this is going to be minus 1 by 1 plus e power minus ZIL square. Okay, and then you take the derivative with respect to this part, the e power minus ZIL. So this is going to be e power minus ZIL and into a minus 1, right? So this is, I think you guys would all be familiar with this kind of calculus. So that's how you just get this, okay? So e power minus ZIL square. So if you look at this, this is actually just, so you can break this down. So there is a 1 by 1 plus e power minus ZIL times e power minus ZIL by 1 plus e power minus ZIL. Right? So I'll just split this up. So this part is exactly the same function, sigma of ZIL. And if you look at it carefully, this is actually 1 minus sigma of ZIL. Right? So 1 plus this quantity is, 1 plus, this quantity plus sigma of ZIL is going to give you 1. Okay, so that's why this holds true. So what we got is dou AI by dou ZIL is just sigma of ZIL times 1 minus sigma ZIL, or it's just AIL times 1 minus AIL. Right? So this is just AIL times 1 minus AIL. Okay, so sigma of ZIL is AIL, that's why. Okay, so that is this part. Now you need again dou J by dou AIL. So that is basically the derivative with respect to this quantity. Now what you need is, AIL is going to get invoked by layer L plus 1. So basically you'll have all these quantities. So basically all these S's are going to call this. And here it's going to get called through ZSL plus 1. So remember ZSL plus 1 is now going to be, it is going to have all the components from layer L, right? So you're going to have W, something like this, WI. So now I is the variable. So maybe let me call it some K. So K is from 1 to, or let me keep it as I itself. So you will see it a bit better. So I is 1 to NL. So there are NL neurons here. So WKS L plus 1 times AKL plus the BS of L plus 1. So this is how you would have computed ZS L plus 1. So now what you need is to compute dou J by dou AIL, right? So which is basically getting invoked here. So what you will do is you will compute a dou J by dou ZS L plus 1, right? Because that's where all these come. So this is WI. Okay, I mixed up the notation. So this is WIS times AIL plus BS. Okay, so AIL is basically coming up in the computation of ZS for every of these neurons in this layer L plus 1. Okay, so that's so how you would do is, okay, I need a really big board. So what you would do is dou J by dou ZS L plus 1 times dou ZS L plus 1 by dou AIL. Okay, so with respect to this, and this you will sum up over all the S's. So that is again the chain rule. That's what the chain rule says. So let me just copy this down, maybe that will help. Yeah. So basically, so this is layer L. And yeah, so what you need is dou J by dou AIL. So again, like, by chain rule, like if you have like multiple functions, right? F of G1x and so on. This is if it's a function of multiple such points, what you would do to find the derivative with respect to x, it's just you will take each of these GIs. So you will take dou F by dou GI, right? So for all the n values, and then you will just take dou gi by dou x. So dou gi of x by dou x. So it's the same idea here. AIL is getting used by all these layers, right? So what you would have had is ZS L plus 1 is summation W I S L plus 1 times AIL. So this quantity times AIL, and all the i's in this network are going to, all the i's in this layer are going to matter, plus BSL. Okay, so this is how it comes. And this will be true for every S. So in every S, this AIL, this particular I is going to come in as well. So what you do is you take all the S's in layer L plus 1. So S is 1 to N L plus 1. Okay, and you take the derivative with respect to dou Z S L plus 1 times dou ZS L plus 1 by dou AIL. Okay, so it's exactly chain rule. Okay, there's nothing else going on here. It's just chain rule of differentiation. And this part is actually what we told as delta S L plus 1. Okay, and this part dou ZS L plus 1 by dou L, can you tell me what that is? So dou ZS L plus 1 by dou AIL. Can you tell me from this one? I just need about 2-3 minutes more. I think I'm again running beyond the time, but let's just finish this up. Can somebody tell me what this derivative is going to be?
WIS of L.
Yes, exactly. So this is WIS of L plus 1. Right? So this is just going to be summation of SS1 to NL plus 1, delta SL plus 1 times W IS L plus 1. Okay, so overall you can bring in these two pieces here and now compute delta IL. Okay. Okay, so delta IL now, so putting this one, this, and plugging it back here, what you're going to get is just AIL times 1 minus AIL from this part, AIL times 1 minus AIL times this summation. So that is of the next layer. Okay, delta S L plus 1 times WIS L plus 1. Okay. Now this delta S L plus 1, remember how it works. Like in the back propagation, what you're going to do is you would have computed deltas for the next layer beforehand. Okay. And so that's why you will have this available with you and so on. That's how it proceeds. Okay. So this is going to be this computation. Okay. And now even the final layer, there is some difference for this last part. Like for this, let's just write that. Maybe this layer L plus 1, right? So layer, the very last layer that you have, layer L plus 1. So here you're going to have, AI of L plus 1s. Okay. There is no dependence on the next, there is no further layer. right? So now when you compute, the only difference will come when you compute this quantity, dou j by dou AIL. So in order to compute dou j by dou z's here, to compute the delta i's of L plus 1, you will need this quantity, dou j by dou AIL plus 1. So there will be just a small difference because the AIL plus 1s directly come in the objective. So remember the J function is defined like this, right? A J L plus 1 minus Yj, right? So this is how you had it. So now when you take dou J by dou capital J by dou, let me just say AI L plus 1, what it's going to have is, this directly comes here. So you will just have 2 times AI L plus 1 minus Yi. Okay, so that's the only change in the last layer. And when you plug this in, right, so what changes is this part, right? So this all remains the same. So when you take delta I of L plus 1, so one part is this, you're going to get 2 times AI L plus 1 minus Yi times this quantity, right? What was that? So times dou AIL by dou ZIL. So that was AIL times 1 minus AIL. So this was AIL plus 1 into 1 minus AIL plus 1. Okay, so that's the only change. So I know, I mean, this is kind of probably it's like too much information to grasp in one class. But what I suggest is like you go through the steps carefully. It's not really hard. It's just the notation. Sometimes you see it first time and it just kills the spirit. But what I want to say is the steps are like really easy. There's no magic happening. It's just you have to systematically sit and derive it. Okay, so that's the only thing, and don't mug up these steps. Okay, you can always rederive it as and when you need. Okay, mugging is not, I don't think it's possible to mug this kind of a thing. Okay, so we'll stop here, and I'll just hang back if there are more questions. Otherwise, yeah, thanks everyone. We'll meet on Tuesday.